Okay, so last time we were discussing the stereographic projections, right? The so on the n-dimensional sphere. Okay, so maybe one thing that's worthy of mentioning is the fact that in the case of a two-sphere, the two-sphere also admits a complex structure, which would mean that by definition that the transition map, so the transition maps in your atlas are biholomorphic and not only diffeomorphic, okay, in the usual sense. Okay, so let us comment on this claim. So we have, in particular, S2 as a subset of r to the power of 3. Yeah, no. Now we may identify this r to the power of 3 with the product of the complex plane with the reals, right? And in this way, we write S2 as pairs of so complex numbers and a real number. And the condition on this set is that the absolute value of this z squared plus u squared is equal to 1. So this is nothing out of the ordinary. I'm sure you can all digest this. Okay, so in the case of the two-sphere, we may define two local charts. So one is, so this is now the stereographic projection, right? One is z over 1 minus u, and the other is psi is, psi of z comma u is equal to z over 1 plus u, right? So now maybe as a comment, phi is now equal to sigma plus, and psi is now equal to sigma minus from before. So from the previous exercise session. Okay. So this is really easy to check. I'm not going to do it. You are invited to check this for yourself. So now, before we try to compute any kind of transition maps between these two local charts on the two-sphere, we observe the following. So if we multiply, so phi of z comma u with psi conjugated z comma u, what we get is, so first of all, in the nominator we have z times z conjugated, and in the denominator what we get is 1 minus u squared, right? Okay, so this is nothing else but z squared, so z absolute squared over 1 minus u squared, but 1 minus u squared is exactly z squared, right? This formula here that I've underlined said it. Okay, so what we get here is 1. Okay. So furthermore, if we write, so let's say theta is equal to psi conjugated z comma u, we may express z comma u as psi conjugated inverse of theta. Okay, this is nothing nothing that you couldn't handle, I suppose. We are just denoting by theta a complex number, right? So a value from the complex plane. Okay, and now if then we may write, so phi of psi conjugated inverse of theta times theta, let's say. Okay, so this would now be what we've written here is nothing else but z comma u, right? Okay, so this whole thing here is phi of z comma u, right? And this thing here is equal to psi conjugated of z comma u, right? Okay, so from before, we see that this is 1. Okay, so this implies that we have phi of psi conjugated inverse of theta is equal to 1 over theta. Okay, so this is what we have been working towards in this exercise. So this now means that so this map is holomorphic, right? Not only is it holomorphic, it's biholomorphic on the complex plane without the origin. Okay, this map is its own inverse, right? So let's write this down. This map is holomorphic on the complex plane without 0. It's even biholomorphic since it is its own inverse. So what this means now is that hence phi and psi conjugated constitute charts of a complex manifold. Okay, so as I've said, now in the case of a real manifold, we demanded that our transition maps between charts are diffeomorphisms, right, in the usual sense. like in the sense of your analysis 2 course. Well, what does it mean to be a complex manifold? Yeah, well, nothing else than we have the requirement that instead of our transition maps being diffeomorphic, they are biholomorphic, right? So I'm not sure if I should write this. I mean, I've commented. Maybe I should write this in a kind of parenthesis. So maybe we should write biholomorphisms instead of biholomorphic. Okay, so this is something that's maybe worthy of talking about. This is the reason why we did it. Now, for you that are maybe interested in these kinds of stuff, you should probably consider the electory subject Riemannian surfaces. I think Professor Forstnerich is the lecturer. Some of you may have already had it, but we are not going to go in any more detail regarding this. Okay, so next up is a remark. So the dimension of any manifold is a well-defined thing. So what do I mean by that? Can anybody answer? And why am I saying this? I mean, why am I able to say this? Does anybody know?
Do you perhaps mean the open mapping theorem?
Yes, this would be the content of the proof, let's say, that the dimension of any manifold is a well-defined thing. So maybe let's write some stuff regarding this down, okay? So So, as I've said, the dimension of a manifold is a well-defined quantity. So this holds not only in the case of smooth manifolds, but also in the case of topological manifolds. So actually, the proof is done in the setting of topology. So let us maybe state the relevant theorem. So this comes from algebraic topology. This theorem is called invariance of domain, and it states that if U is an open subset in R to the power of n, and F from U into Rn is a continuous injection, then f of u is open in R to the power of n, and f is an open map. So this would mean that it maps open sets to open sets. Okay? So because of this, it's a topological embedding, which would mean that it's a homeomorphism onto its image. Okay? So, of course, if you have an injective map, you may form its inverse, right? But this inverse is only defined on the image f of u. So now this theorem states that this image is continuous as well if the map f is continuous. So this is with respect to the relative topology on f of u. Okay, so the proof of this requires some stuff from algebraic topology, which we are not going to do. So for proof, maybe see Hatcher, page 172. Okay, so let's try to apply this theorem in our context, okay? Let phi of u to Rn and psi from, let's say, V to Rm be two charts on our manifold. So, and suppose, of course, that they overlap, okay? Okay, now suppose that n is greater than m. Now we may form the composition from our Rn into Rm and back into Rn by inclusion. Okay, so this ins would mean that we are like this is really something something trivial. So we're just putting zeros in the last n minus m places. Okay, this composition is injective and continuous, right? So now we utilize the above theorem. So by above theorem, its image is open, right? But now, what is the image of this map int? It's of course just the Rm times 0 to the power of n minus m, right? But image of int is equal to Rm times 0 to the power of n minus m. Any subset of which cannot contain an open ball in Rn. So any open Euclidean ball. Maybe I should write n ball. So its image cannot be open, right? The image of the above map. So this would be the end of the proof that there must hold m is greater or equal to n, right? Now just in the other direction, right? By using not psi of phi to the power of -1, but phi of psi to the power of -1, we get the we get the result that m must be less or equal to n, right? So this now implies that m is equal to n. Okay, so this is maybe something that that may seem obvious, right? Of course, one would be inclined to think that you know that the codomain of the chart must always have the same the same dimension, right? It must always be the Euclidean space of the same dimension, but this this now here is a rigorous proof that that this is so. Okay, so let's okay, now I'd like to give you like an option. Would you rather try to define a smooth atlas on the projective real space and dimensional, or would you rather that we discuss products of smooth manifolds?
Products.
Okay. So this is coming from someone that has already seen the construction of the charts on the projective real space, right? We had, last time we were at the second exercise, I think. So now this is the third exercise. So suppose M and N are smooth manifolds. At most one having a boundary. And now let's say that n has a boundary. Okay? So we want to prove that m times n is a smooth manifold. So does anybody have an idea of how to form like the smooth structure on this product?
Probably just the open sets are probably just going to be the products of M and N. And then the charts, probably just the first component of them is going to be U alpha, for example, and the second one is going to be psi beta, one for M and the other one for N.
Yeah, so what you're saying is, first of all, topology should be the topology of boxed sets, right? So the boxed open sets. And secondly, the construction of charts should be something natural, right? This is what I've inferred from your from what you've just said. Okay, so let us indeed write some stuff down. Topology. So this is the usual topology on m times n. Open sets in m times n are unions of sets of the form u times v, where u is open in m and v is open in n. So maybe something that you should notice is that because m times n is a finite product of topological spaces, this is the coarsest topology such that the projections are still continuous. Okay, and of course the projections, the projection maps that I've declared above have the obvious prescription. I'm not going to write it down. So is this prescription not obvious to anyone? Okay, I'll take that as no, everybody gets it. Okay, so let us try to define the smooth atlas on the product. Okay, so first of all, we have to pick atlases, smooth atlases on M and N, right? I'm just going to write it as such. UI phi I runs in the index set big I. And Vj theta J runs in the index set big J. A smooth atlas on N. Okay, so now we define the smooth atlas on the product in the natural way. So this is a family of pairs, ui times vj and phi I times theta j. So now j and I must run in the correspondent index sets, right? So what is this map here? So this is defined as phi I times theta j. It goes from ui times vj into phi of ui times theta of vj, and it is defined as the map. So let's denote the points in M and N as X and Y, right? So this is from M, this is from N, or from maybe UI and VJ would be better. Yeah, well, we don't have much choice. Okay. So this is the definition of the charts on the product. So what do we have to check now?
This is smooth.
Not really.
The transition maps.
Okay, the transition maps would be one thing. Also, we would have to check that this phi I times theta j is a homeomorphism, right?
Yep.
Okay, but to see that this map is a homomorphism, so phi I times theta j homomorphism. Just note that phi I times theta j inverse is nothing else but phi I inverse times theta j inverse. Okay. And of course, since phi I and theta j are homeomorphisms, this map is a homeomorphism with respect to the product topology on M times N. Okay? And as Grega mentioned, we also have to check that the transition maps in this atlas are diffeomorphisms. Okay, so how do we do that? Yeah, well, we just have to pick not only phi I and theta j, but we also have to pick, let's say, phi I1 and theta j1, and also phi I2, theta j2, right? So we pick two or four indices, two from each index set. Okay, so what we have to write down is the following composition. So this is the first map, and then we have to compose it with phi I2 times theta j2 inverse, and we have to check what this is, right? But this is nothing else than, so phi I1 times theta j1, and compose it with phi I2 inverse times theta j2 inverse. Okay, but now this is easy to see that this is nothing else but phi I1 of phi I2 inverse times theta j1 of theta j2 inverse. Okay. So the fact that transition maps are diffeomorphisms follows from the fact that transition maps in each manifold are diffeomorphisms. So okay, this may seem like a triviality, but it's something that it's nice to do. Okay, it's nice to see this procedure at least once. Okay, so the last thing that we are concerned about here is the boundary. Okay. So can you think of a counterexample when M times N is not a smooth manifold if both M and N have boundaries? I mean, there is a reason, right, why I've written here that at most one has a boundary.
maybe if we take two closed intervals and their product, it's going to be a square.
Exactly.
It has corners, and
Yeah.
that isn't like flat or something.
Precisely. And the points in these corners, they do not admit neighborhoods which would be diffeomorphic to the upper hemisphere or upper half plane, right? So let's write some stuff down regarding this. So in the category of topological manifolds, there is no issue. One may prove, so we're not going to do this. So one may prove that M times N is a topological manifold even if both M and N have boundaries. So, and there holds, so the boundary of M times N is then partial M, so the boundary of M times N and union M times the boundary of N. Okay? So this is in the topological category. But now in the smooth setting, as Jaka said, we get to an issue. So the product of two intervals is a square. Okay? And now this, for example, this point here, of course, every neighborhood must have such a set as a subset. So this would mean like a disk intersected with the square, but this disk is now centered in the corner, right? So this neighborhood is homeomorphic to R2 greater than 0. So this is the upper hemispace, right? So this would mean R times 0 infinity. But it is not diffeomorphic. Okay. Well, however, if just one of them has a boundary, say N, there holds. So this is from the above formula, from the formula for the boundary of the product. There holds that the boundary of m times n is equal to m times the boundary of n. So this follows from above formula, right? And why? I mean, how do we see this? So if P is from M, and if Q is from the boundary of N, and let's say that U phi and V theta are neighborhood charts, so this is a V. So this is an abbreviation for neighborhood, NBD. What we get is, so phi times theta of U times V is equal to phi of U times theta of V. And now this phi of U is, so this depends on your definition of what a manifold is. So I would like to say that this is just R to the power of M, where M is the dimension of your manifold M, right? And this would be Rn greater or equal to 0. Okay. So, but now this is Rm times Rn greater or equal to 0. But now this is diffeomorphic to Rm plus n greater or equal to 0. Okay, so this greater or equal to 0 index means that we are setting the last component of our Euclidean space to be non-negative.
So basically, the issue is that there is no manifold where the last two coordinates are greater or equal to 0. You know what? Forget it.
Yeah,
I get it.
Yeah. That's precisely the issue. Yeah. The issue is that so, for example, translated in the context of maybe two-dimensional spaces, 0, comma infinity, where 0 has the closed interval, right? The closed closed bracket. This thing squared is not diffeomorphic to R times 0, comma infinity, right? You cannot, so maybe the key thing there is no diffeomorphism that takes you from this space into this space, right? So this is where the problem of manifolds with corners is.
So in this case, diffeomorphisms are defined how? By extension to an open neighborhood or something?
Yes. By extension to an open neighborhood of a point. I mean, this is how it's usually done. Now, maybe to be a little bit more pragmatic. So one may always define tangent vectors, for example, on the boundary of this r times 0 infinity. Okay, and this is done with, for example, outward pointing vectors and inward pointing vectors. Okay, so you could have, for example, a path in r times 0 to infinity that reaches this boundary here. Okay, this line in the bottom. Okay, and its derivative would be nothing else but a one-sided limit instead of a both-sided limit, as we're used to in the context of open subsets in the Euclidean space r to the power of n. Okay, so the concepts on this boundary become like one-sided. Okay, the limits become one-sided. They aren't two-sided, both-sided limits anymore. Okay, I'm not sure if I said this concisely enough for you to understand, but yeah, the boundary is always something a little bit evasive in the context of manifolds. That's the whole reason, for example, why such things as Stokes' theorem are a little bit tricky to prove. Not everything is obvious. Okay, you have to somehow make sense of this boundary and orientations on this boundary and so on. Okay, I see that I'm already in the break, so let's have a break at this point and continue at let's say 15 past 11. Ok, bi nadaljevali. So let's continue by yeah, well, we don't have much choice at this point, really. We're still in the process of defining the basic concepts in the smooth category, right? So right now we were concerned with objects in the smooth category. Okay, so now we have to somehow define maps in this category, right? And these are smooth maps. So we have to define what a smooth map is between two manifolds. Okay, so let us make a definition. So of course, this is the above exercise is finished, right? We won't say anything more regarding the boundaries. Let M and N be smooth manifolds. So a map, we usually denote it by G because of the fact that now it's just a letter. It doesn't even matter. I won't even give an argumentation why I'm denoting this by G. A map G from M into N is called smooth. So does anybody who hasn't yet had the analysis on manifolds course reckon how we would define smooth maps? How about those who had analysis on manifolds?
So we compose it with appropriate charts.
Yes.
So we get a map from Euclidean space to Euclidean space.
Yes, of course. So a map G from M into N is called smooth. If for any charts, let's say U phi on M and V theta on N, the map, and we usually denote this by G hat. G hat, and this must go, yeah, so this is now something that is like tricky to write down, the domain and codomain, because we have to like draw a picture before we do that. So let's just form a composition, and then we'll discuss what the domain and codomain of this map is. So if the map theta of restriction of G to U cap theta to the power of -1 of V and of theta inverse, phi inverse, if this map is smooth.
Sorry, what is the pre-image of V under theta?
It's a subset in M, right?
But doesn't theta go from M to Euclidean space?
Oh, yes, sorry. This should be a G. This should be a G. Okay, so let's draw a picture here. So we have, like, let's say this is a manifold M, right? And now we have a map G. So, and we have another manifold here. These surfaces are always the same for me. I always draw them in the same way. Okay, so we have this this map G, and now we have, like, let's say a subset U here. This goes via phi into, let's say, r to the power of m. Okay, now on the other hand, let's have here a chart V, I mean neighborhood, the domain of this chart here, and we have theta here, right? And this goes to r to the power of n. Okay, so now we have to consider the pre-image of V via the map G. So this is pre-image of the set V via the map G. Okay, and we are concerned about whether this composition here is smooth, right? This is our definition now. So this map here is what is called G hat. And of course, we have to restrict it to an appropriate domain, right? So what would be the appropriate domain of G hat is, so G hat is a map, we are declaring it just now, is a map that goes from the subset of the Euclidean space r to the power of m, okay? And this is now U cap G inverse of V. Okay, and it must go to r to the power of n. Okay, so now here you see that we are taking the pre-image of the map V via the map G. And now this is the reason why we sometimes also require the map G to be continuous in advance as a map between two topological spaces. Okay, so for this to be an open subset of r to the power of m, or r to the power of m greater or equal to 0 if m has a boundary, we sometimes require G to be continuous. So okay, now because we have this definition of a smooth map between manifolds, we have objects and maps in the smooth category, right? So it's always useful to approach a given field of mathematics via the category theory, where you are building the bottom up. So yeah, while you are building the theory. Okay. So what would it mean for G to be a diffeomorphism? Let's define that. So a bijection G from M into N between smooth manifolds is a diffeomorphism if G and G inverse are smooth. Okay. So this would mean an isomorphism in the category of smooth manifolds, right? Okay, so now let's maybe do something. Let's maybe connect these concepts that we've just seen. So the concept of a smooth map and the concept of a product of two manifolds. Okay. And we're going to do this in two exercises. So first of all, a definition that maybe physicists in the audience are eager to hear. Let's define a Lie group, what a Lie group is. Okay. A Lie group G is a smooth manifold that is also a group So what additionally has to hold for this to be a Lie group? Can anybody tell me?
For what to be a Lie group?
For G. So G is now currently it's a smooth manifold and a group. So what would make it a Lie group?
So the operation of so basic operation need to be smooth with respect to no, they have to be smooth.
So they have to what?
Be smooth.
Yes,
Smooth
with respect to the smooth structure.
structure. Yeah.
So how should I write this? A Lie group G is a smooth manifold that is also a group.
Smooth operations.
So I'm gonna make a semicolon here. The multiplication, let's call it M, G times G into G. So and inversion, let's call it inv, that goes from G to G, are smooth maps with respect to the smooth structure on G. Okay, so we've defined products, so we know what charts on products are. So now everything is well defined here, right? The notion of multiplication map being smooth and inversion map being smooth, these are all well-defined concepts right now. Okay, so first of all, we're going to make a note here. Firstly, inversion, right? Inversion is something that has also an inverse, right? Inv G into G is defined as inv of G is G to the power of -1. What is its inverse?
Itself?
Yes. Since inv to the power of -1 is equal to inv, this map is automatically a diffeomorphism. So in a Lie group, right? Furthermore, we have left and right multiplication, right? For any G in G, define LG as the map M of G comma dot. Okay. Would you say that this map is a diffeomorphism?
Yes, because the inverse is the composition with the inverse, which is also a smooth map.
Exactly. So this is also a diffeomorphism. So we abbreviate diffeomorphism by diffeo, since LG -1 is its inverse. Okay, so this is a map, obviously, that goes from G into G, right? Okay, so now we see that that these that these maps are diffeomorphisms. So let us go on and indeed solve an exercise now. There's been a lot of theoretical exercises like at this point. So let us now turn to a specific example. So if I'm not mistaken, this is now the fourth exercise, right? Yes. So the fourth exercise would be to show that GL and F, which we've defined in the previous exercise session, right, is a Lie group. So smooth structure is already done. We just write a tick group structure. Of course, this is just matrix multiplication and inversion. Okay, so now we have to show that these two structures are compatible. So how do we do that? Let's first touch multiplication. Why is multiplication a smooth map?
Wouldn't multiplication just be polynomials in each component which are smooth?
Yes, exactly. So we have to realize that matrix multiplication is already done in the more in the more general set of all matrices, all n times n matrices, right? So we have m that goes from f n times n times f n times n into f n times n, right? So this is a smooth map because because its components are polynomial functions of components of the two matrices that are being multiplied, right? So since its components are polynomial functions, of the components of the matrices that are being multiplied. Okay. How about inversion? I forgot to comment on the multiplication now in GL and F. Why is the multiplication in this group smooth?
Because it's smooth for matrices in general.
Yes, but we need like an additional argument here now. How is smooth structure on GL and F defined? If you recall.
It's defined as the substructure in the general matrices, like with intersections.
Okay, so GL and F is open, right? That's probably what you were referring to.
Yes, it's open.
So GL and F is open in the set of n times n F matrices. So the multiplication in this group is just the restriction of the multiplication in the the set of all matrices, right? So M in G, L, and F is just the restriction. So the appropriate restriction of the domain and codomain to an open subset, right? Of f n times n. Okay, so this is a whole lot of words to say barely anything. Now finally for the inversion. Why is inversion smooth now?
Because the determinant is also a polynomial function and its inverse is defined. And the inverse of it's smooth, all of it is smooth.
Okay. Yes, I mean, it's kind of obvious, right? But we would at least want to use like a specific, at least an argument using a specific rule for matrix inversion, right? And that rule has a
There,
name.
yeah, well, I don't know what the name is, but yeah, there's a formula that that defines the element of the inverse matrix by the determinant of the submatrices and
Yes, exactly.
other elements.
So that's by using cofactors, right? They're called cofactors or something like that. So this rule is called Kramer's rule. So I'm just gonna write similarly as for multiplication, but now using Kramer's rule. So as Grega said, we get to the components of the inverse by dividing by the determinant and also by cofactors of the matrix that is being inverted, right? Okay, so that's more or less the argument. Okay, so now that we have solved this exercise, I'm not sure. In the last exercise sessions, we said that G, L, and C is connected, right? But we didn't give a proof. Do you know how the proof would be done now that we know that GL and F or GL and C is a Lie group?
Last time I was thinking if we use singular value decomposition,
Okay.
then we get a diagonal matrix that's obviously connected to the identity.
Okay.
And we get two unitary matrices and, well, okay, unitary matrices you can kind of rotate to get the identity. That should be probably cleaned up a bit, but that's basically the idea.
Okay. So maybe let's have a small comment here. G, L, and C is connected. So Yaka is on point here. So we have the singular value decomposition. It's also called Schur's decomposition. So every matrix A from G, L, and C is so podobna, which in English would be
Similar.
Similar or equivalent or something like that. Yeah, is similar to an upper diagonal matrix. So this is called Schur's decomposition. Okay, so now the upper diagonal matrices are connected, path connected to the identity. Okay, these are path connected. And so conjugation in a Lie group is a diffeomorphism, similar to the left and right multiplication. Actually, conjugation in a Lie group is nothing else but composition of left multiplication, say by G, and right multiplication by G inverse, right? So, and conjugation in any Lie group is so a diffeomorphism, more specific, I mean, if it's a diffeomorphism, it's obviously a continuous map, right? So the general linear is somehow it's an image of, or maybe I should say, a union that runs through all Hermitian matrices of the image of the upper diagonal matrices via conjugation, something like that. Okay. I'm not sure how to write this now. So GL and C is a union, and now H should be like a Hermitian matrix. So the Schur's decomposition gives us a similarity relation, but now the matrices via which these are similar are Hermitian, right? Okay, so what we get is CH of upper diagonal. Let's denote them as such.
Are you sure they're Hermitian? I don't know, Wiki says they're unitary.
Oh, unitary, yes, yes. They're unitary, not Hermitian. I'm sorry. So this should be like U from UN, and we should have here a U. Okay, so the argument is something like this. You should fill in the details yourself. I did this once, and I just somehow remembered that this is something that we could do at this point, since we have all of the ingredients. So I'm trying to somehow remember what are the key steps. Okay.
What's CU?
Conjugation by U. Okay.
No.
So this is homework. Fill in the details. Okay. So this was one exercise that to show that this general linear n times n matrices is a Lie group. The next one would be that to show that like natural inclusions are smooth maps, natural inclusions into the product. Okay, so let's let M and N be smooth manifolds. And let P be from M and N, Q be from N. Okay, so we have to show that the inclusions ins MQ which goes from m into m times n and is given by int m q of x is equal to x comma q. And also the other one are smooth. We have to show that these two maps are smooth.
How are we going to do that?
Yeah. Do you have an idea?
Well, one of them is an identity and the other is a constant.
Something
So,
like that.
and a constant function is smooth,
Okay, so
like trivially.
should we do this in charts, maybe? Should we try to utilize the whole abstract nonsense that we have in this context of smooth manifolds to try to show that these two maps are smooth? I mean, that's by using definitions, right? So that's a good exercise from using the definitions. So I would again write, let ui phi I in I be a smooth atlas on M, and Vj theta j runs in index at j, smooth atlas on N. Okay. So what we need to check is the following. So first of all, we are obviously going to do this only for one of these above maps. The other one is similar, right? So we have M goes into M times N, and here we have ins MQ. Okay, so now here we have a chart. Let's say UI. Okay, and via phi I, we take it to phi I of UI. So this is an R to the power of M, let's say. Okay. On the other hand, we have here a chart UI times Vj, and maybe now this I should have like I don't know, some other index or something like that. Maybe let's write a 2 here and a 1 on the other side. So everywhere on the left side you should write I1, on the right side you should write I2. Okay. So here we have the chart phi I2 times theta j. Okay. So this maps to phi I2 of UI2 times theta j of Vj, right? And now we have to check that this map here that goes like this is smooth, right? It would be like maybe fine to denote this by ins m q and hat, right? We were writing hats before in order to denote the whole composition of maps. Okay, so we need to check that this composition is smooth. So let's try to write it down, right? We have phi I2 times theta j of ins mq of phi I1, right? Oh, and inverse must be here, and let's pick an element of r to the power of m here. Okay, so x here now is not an element of m, but rather it is an element of phi I1 of u I1, which is just something in r to the power of m. Okay, so what we get here, this is kind of a triviality, but nevertheless it's instructive to do it. Phi I2 times theta j. Okay, and now we have to use the definition of the map ins qm, and what we get is phi I1 inverse of x on the first place, and on the second place we only get a q, right? Okay, so here what we get now is phi I2 of phi I1 inverse of x, comma, theta j of q. And now we're almost done. We just have to comment on one thing, and that is that, what is that?
Both components are smooth, so this is smooth.
Yes, both components are smooth, and why is the first one smooth?
Because n is a smooth manifold.
Yes, because the transition maps in any smooth manifolds are smooth, right? So smooth, since M is a smooth manifold, and this is smooth as a constant map. Okay, and the second map is Pn similarly. Okay, so I see that we've come to an end of our exercise sessions. So maybe one thing, I'm just going to write the instructions of the next exercise, and it is to show that Sn, so the inclusion of Sn into Rn plus 1 is smooth. Actually, we could do it in a matter of a couple of minutes, but let's conclude the exercise sessions for today. You may try to solve this exercise at home because you have all of the ingredients that are needed. Okay, so the charts on any n sphere are known to you by now, and you know what the inclusion map does. So you have all of the ingredients in order to check that this map is smooth. Are there any questions here?
what does it mean for a mapping to be smooth?
What does it mean? What?
For a map to be smooth, what's the definition?
Didn't we write it above?
Did we?
Yes, we did, yes.
So it's right here with all the fancy pictures.
No, this is in the definition. It's what?
Yeah, this
But
is a definition of a smooth map between two smooth manifolds.
yeah, but I mean, what's the definition of a smooth map?
Oh, you mean a smooth map between Euclidean spaces?
Yeah, sure.
Yeah, well, all of this is like what I had in mind when I said that a prerequisite knowledge is so multivariable calculus, right? So all of the partial derivatives of a map must exist and they must be smooth. I mean continuous.
Okay, thank you.
That's the definition. So as a map from r to the power of m to r to the power of n, for example, right? You know what the partial derivatives of component functions are. So, and if this if all of them exist and are continuous, then we say that a map between Euclidean spaces is smooth. Okay, so this is smoothness in the usual sense that you were asking about on previous exercise sessions. Okay. Is it clear?
Yes, it's clear.
Okay. Any other questions? Okay, if not, let's conclude these exercise sessions and I'll see you next week.
Goodbye.
Bye-bye.
Bye.
Bye. Bye.
Bye.